Alright, welcome to COVID calculus number 6. In this case, we're looking for the change in distance for hypotenuse given the change in speed of or change in distance of a height, let me put it that way, of a side. So what we have is a baseball diamond. Baseball diamond, what it's saying is that a ball is thrown from a pitcher mound. So we have our pitcher mound here. The ball is thrown towards home plate. Okay, so you got home plate right there. A batter comes and hits the ball directly in the air at 50 miles an hour, excuse me, at 60 feet up. So we have a distance of 60. The speed is 50 feet per second. The question is asking how fast is the distance between the ball and second base changing. So we'll call this C. A squared plus B squared equals C squared. We're looking for the change in C. So that is my question there. Looks like a number 3. Let's rewrite my question mark there. Okay, so this is what we're looking for. We don't know this distance, first off. We don't know C. We don't know a lot of things. So we're going to have to start from the basics. So first, we're going to actually start with the idea of a baseball diamond. So a baseball diamond, if you're not familiar, it actually gives us a little insight. Let's say we have our pitcher mound in the middle here. We got second base, and I'll do my best here, right here. First base right here. Home plate right here. And third base right here. And again, I did my best. And I'm going to go ahead and connect those lines just to give us an idea. Well, it happens to tell us that the distance between each base is 90 feet. So each side is 90 feet. So we have a four-sided thing where every side is the same. That is a square. So we have a basic square, even though it's called baseball diamond, it's baseball square. And on a square, we have all sides equal to 90. They're all the same. And we have all angles equal to 90. What we need to figure out is these in-betweens here. So that line, that line, that line, and that line. I forget, I'm a little off there. So what this does is break it into some triangles, and really what we're doing is kind of drawing diagonals across this square, right? If I were to draw this a little bit more accurately. Well, if I'm bisecting these 90-degree angles, that means every one of these angles here is 45 degrees, right? 45. This one's 90. All these are 90. I'm going to draw a box just for 90-degree angles there. So this gives us some insight here. So again, we need to find this. We don't know this yet. So we're going to kind of break this up. So if I pull out one of these triangles, I get this. This is 90. This is 45 degrees. And because it's 45 degrees, I also know that this must be 45 degrees, right? Because if I have a 90-degree angle, one of the sides is 45 degrees. They have to add up to equal 180. So I find out that the other one also has to equal 45. If these two angles are the same, it means these two sides are the same. So typically if you're trying to find a side, you're going to use Pythagorean Theorem. A squared plus B squared equals C squared, right? Except here, let's say this is A and this is B and this is C. A and B are the same. So I can rewrite that as A squared plus A squared equals C squared, right? Well, now I have 2a squared, and just add them up, equals c squared. And I happen to know c. C is 90. So now I have 2a squared equals 90 squared. Well, 90 squared is 8100 equals 2a squared. I can divide both sides by 2, and I get a squared equals, that's 4050. And then if I take the square root of both sides, I get a equals, and I believe it's 63.64 if you plug that into a calculator. So I get a value for my sides here. Well, coming back up, that was to the pitcher mound. You see, that was this side here, and that was this side here, and this side here. So this is 63.64. But I have two of those. I have from the pitcher mound to home plate, and I have from the pitcher mound to second base. So what I need to do is multiply that by 2. And I'm going to pull out my calculator real quick. We get 63.64 times 2, 127.8. So I'm going to redraw this triangle here. We got here, this is 127.28. This is my unknown. And this is set to 60 right now, right? With a speed as well, if I wanted to do that. Okay, so I'm getting there. Everything is going smooth thus far. Let's go ahead and try to solve for C, right? Because really what I want to find is a formula that solves for C to which I can find the derivative of, right? I'm trying to find the change in C. So let's move over. There's our new triangle. I know that a squared, just as before, plus b squared equals c squared, right? Well, let's call this a, let's call this b, and that's c. So we have 60 squared plus 127.28 squared equals some value squared. Well, let's add that up. So again, I go to my calculator. Well, 60 squared is 3600 plus 127.28 squared, where are you? There you are. That's 16,200.2. Okay, let's add those up. 3600. That's going to equal 1980.2. But I need this solved for c squared, right? So I need to actually find the square root of that. So the square root of that is, let's do it. Square root equals 140.71. Okay, there's my side. So c equals 140.71. So first I need to ask, does that make sense? And it does. You have a side that's relatively short, your side that's relatively long, and then c will be somewhat longer than that longer side, right? The hypotenuse is always the longest side. It's not overly so, it's within the same range. So I think that makes sense. Okay, so now what we're trying to do is find c prime, right? Derivative of c. Oop, not c squared. C prime. Okay, and we also happen to know that the question asked for how fast is it changing. So it's some speed. And it also gave us that the height was changing 50 feet per second. So it's per unit time, right? So I'm looking for c prime, but c prime is going to be the derivative of c with respect to some unit time, right? That's what I'm looking for. So let's find that formula. So that formula is going to be c equals, and I really am just plugging the values in here, right? But I'm going to have the square root, because I'm solving for c, of a squared plus b squared. Okay, this gives us the value for c. Now the question we have to ask is, we're going to do a derivative with respect to time. So the next question we have to ask, and again, we considered this to be a and this to be b. Which of these is changing in time? Are they both changing in time? Is only one of them changing in time, or is neither changing in time? Well, over time, if the ball continues to go up here, this isn't changing. So this is a constant, right? Well, that's handy. That means that value is just basically going to go away if we take a derivative, right? This, however, is changing in time. So let's say this is height. Let's say this is also called height. You know, whatever you want to call it. So what we're going to do here is we're going to say, okay, the derivative. Let's rewrite this just a little bit. We have c equals. I'm going to do, instead of square root, I'm going to do a squared plus b squared to the 1/2. I always like writing it that way because 1/2 is the same thing as saying square root. And this gives you a little bit more freedom when you go to actually take the derivative. So we know that this is a constant. So if I take the derivative of c with respect to time, I'm going to have the derivative of this outside value, which is going to be, you pull it on the 1/2, and you have the inner half as is. It's going to be a squared plus b squared to the negative 1/2. And then you multiply, this is the chain rule, you're going to multiply by the derivative of the inside of those parentheses. So if I take the derivative of those parentheses, 2a will become, a squared will become 2a, and this is going to be the derivative of a with respect to time, because we know that a is changing in respect to time. And then b just turns into nothing. B is a constant. right? So that just goes away. Well, cool. We have our change in height, dA, with respect to dt. We have what we're looking for here, and we have everything else fit in. So what we can do is start plugging stuff in. So we're looking for, so let's dc over dt is 1/2. We're looking for a, which is that height, when it is equal to, what is it, 60, right? So I can plug in 60 squared. Plus, b is, what is it, 127.28. I got to square that. Times 127.28. That's going to be, again, I actually already had done that, so I could have written it down. 0.2. That is all to the negative 1/2. And then 2a, again, a is 60, so that's going to be 120 dA dt. Oh, and we actually know dA dt. Let me back up. It had already given me the speed here, right? This was the derivative to this side with respect to time. So I actually already know that. That's times 50. So I can plug that in. Okay. We're getting close. So we have dc over dt equals 1/2 times, this is going to be 1 over the square root of 3600 plus 16200.2 times, what is 120 times 50? 6,000. Big number. Okay, getting even closer. So I'm going to simplify this 1/2 and the 6,000. So dc over dt equals 1/2 and 6,000 becomes 3,000. I can actually put that in the numerator, and we get, if we add 3,600 to 1680.2, we get 19,800.2, and that's going to be the square root. Okay, let's do it. What is the square root of 19,800.2? That is 140.7. Would you look at that? So we get 3,000 over 140.7. 3,000 divided by 140.7 equals 21.3 feet per second. All right. Okay, that was quite a bit. I hope you followed. So if we back out, let's go ahead and start over. We start with the question of a baseball that's shooting up in the sky at some speed, and then the question is asking from some point far off in the distance on the ground, as it increases in distance vertically, what is the distance that it's changing on this diagonal? And in order to do that, we have to figure out what the horizontal is. So we got to actually kind of figure out a few more points. So we start looking at the baseball diamond. Given the fact that we know the distance between bases, and the fact that each base is equal distance from each other, we learn that it's a square. And when we divide that up, we can then find the sides of these little cross sections. If we find those cross sections, we can find that base. So once we find the base, we pull it out over here, and we find all sides. So 140.7, 60 was this side, and 127.2 was this side. Then we actually have to figure out, okay, we are looking for the change in this diagonal. The change of anything is also a derivative of that. So we're looking for the derivative of the hypotenuse. More importantly, we're looking at the derivative of the hypotenuse with respect to time. So we brought in this new variable of time. The reason we know that is because it's asking for a speed, and speed is inherently including time. So in order to solve for this, we have to find a formula that solves for c, which is right here. We used just the Pythagorean Theorem, but we took the square off of c by pulling a square root on the other side. We then simplified that formula. Instead of using a square root, we have a to the power of 1/2, which is saying the same thing. And if we continue down, let me zoom back in. Whoop. If we continue down, we start talking about, okay, we're taking the derivative with respect to time, dc over dt. We pull down the 1/2 Like we take the derivative, this chain rule of the outside first, we take the derivative of that, the 1/2 comes down, we subtract 1, we leave the inside as it is, and then we multiply that by the derivative of the inside. We already found out that b squared, which is the base here, does not change. The distance between second base and home plate, no matter how high the ball goes, does not change. So we leave that. That disappears when you take the derivative of the inside. And we happen to know that dA over dt, the change in that height, is changing in its own respect to time. It's not directly linked to dc. It's changing up kind of on its own here. We're looking for that relationship between the two. And what's great is we know the distance. The distance is set to a point where it is 60 feet away. We know the speed. It's changing at 50 feet per second. So we're able to plug all those values in, and then we're able to solve for it. Once you solve for it, your solution is the derivative of c with respect to time, or the change in time, or the speed. And we find out that it's moving at 21.3 feet per second on the diagonal versus 50 feet per second on the vertical. And it would make sense that it would change a lot less, because if you think about it, this is moving at a direct line, whereas the other one's moving at an angle, and it has a little bit more of a lag behind it. Anyway, I hope that was of interest or of help.